My name is Arjit Sau, and I'm a PhD student at Chennai Mathematical Institute. So we have built a tool for counting and sampling for bit vectors. We call it CSV. And today's talk, I'll be talking about this work. So this is a joint work with my advisor, Kuldeep Mill. He's from University of Toronto. So let's get started with the definition of the problem. So given a bit vector formula F, the task of counting is to count the number of satisfying assignment for that formula. So in most of the practical cases, we do not need a exact count. If we have an approximation of the count, we are generally happy with that. The task for sampling is to return a solution randomly from the set of solutions. So for all the satisfying assignments, the probability of returning that in a sampling call is exactly 1 over number of solutions. In case of sampling also, we do not generally want an exact sampling. If we have this probability within some epsilon bound, then we are happy with that as well. So the theory of bit vectors is a popular theory, and that is pretty much used in case of model checking and verification domain. And when the question becomes a quantitative question, in case of this model checking and verification, like how many bugs exist and so on, then the question is no more a solving question in case of theory of bit vectors. In that case, the question becomes a counting problem in bit vectors. Also, the counting of bit vectors has some applications in this cryptography, like automating the development of Trojan ciphertext attacks. And in case of sampling, there has been applications in case of constant random simulation and things like that. So it's something that has so many applications. We are not definitely the first people to look into the problem. There has been a set of works on counting of bit vectors. There has been a set of works in case of sampling as well. But in this work, we want to look at that there has been a significant development for CNF counting and sampling. That is the problem of counting of propositional formulas. So there has been a significant improvement for last 10 years on this domain. We wanted to see how much we can translate that improvement to the domain of counting and sampling for bit vectors. So given this, our framework looks pretty simple, that given a bit vector formula, we will bit blast that formula such that the bit blasted CNF formula will have exactly the same number of solutions for that the bit vector formula has. And after we have this bit blasted formula, we will pass that bit blasted formula to a propositional model counter, and our model counter will return that count. So we built our tool, we call it CSV, on top of the SMT solver STP. So we turned off all the simplifications and rewrites to make sure that the bit blasting procedure is a count preserving procedure. And this STP has these different SAT solver backends. So we plug in the model counter approximacy in place of this SAT solver backend. So our tool CSV essentially takes the formula and returns the model count. So there has been a significant work in both in terms of bit blasting and model counting. So we tried all of them. We tried different bit blasting techniques. We tried all different model counters, like exact model counters, approximate model counters. We also did some kind of preprocessing. So there has been before passing the CNF formula to the model counter, we pass it through a preprocessor. We tried different preprocessing and without preprocessing. And the observation was that these different combinations, so now there can be different configurations for CSV. So we picked the best performing setting for CSV. And the best performing setting was this technology mapping, then Arjun, then approximacy. So another observation there was that the configuration in which you are adding these components together makes a real change. For example, like as I was saying, that this technology mapping plus Arjun plus approximacy is a best performing configuration. If you remove Arjun from it, then the performance degrades a lot. But if you add Arjun before SAT TD, its performance degrades. So the configuration in which you add or remove the different components or change the components that makes a change. So in case of sampling, the framework is also pretty similar. We have this count preserving bit blasting. Now we pass that bit blasted formula to a CNF sampler. Now the CNF sampler returns a CNF sample. We pass that CNF sample to the STP again. So STP knows the mapping between the bit vector variables and the Boolean variables. So from the Boolean sample, STP can construct the bit vector sample. So we have two different modes for sampling. Like so one we call as almost uniform sampling, for which we use the tool Unigen. So in this mode, the sampler returns the samples with theoretical guarantees, and this uses this hashing based approaches. And the second mode is more interesting, that is called the uniform like sampling mode, in which the samples itself do not come with the theoretical guarantees, but the samples passes the distribution testing based tests. That means, like, if you give me a set of samples from this uniform like sampler or the almost uniform sampler, there is no way to differentiate which set of samples is coming from which sampler. So the sampler we use for this uniform like sampling mode is called the CMS gen, and that is a tweaked version of crypto-MiniSat, which uses random heuristics inside it, like random branching, random restarts, random polarity. So this crypto-MiniSat behaves pretty randomly. So the takeaway here is, like, this uniform sampling mode is much faster in practice, and if you do not care about the uniformity guarantees, then you should use this uniform like sampling mode. So let's come about the results. So we compile a set of 668 benchmarks from these domains use cases. We run the current state of the art, and it solved 143 instances. And we run CSB on top of on these instances, and it solved 647 instances. So we get more than 4 times improvement on this set of benchmarks. In case of sampling, we also get similar performance, like this almost uniform sampling mode that solves 641 instances out of 668 instances. And the median runtime to generate 500 samples is 74 seconds. In this uniform like sampling mode, it is much faster. The median runtime is 1.24 seconds, and it solves almost all the instances apart from 6 instances. So to conclude, we have built a very efficient tool for counting and sampling for bit vectors. So in my PhD, I am looking at counting and sampling for other theories as well. And in SMT, there can be, like, many different questions for counting and sampling. So if you have any applications for this, or if you have some other questions that I should look at, we should chat. So thank you. Our tool is available online. The paper is also here. And thank you for your attention.
Questions? So what was the role of technology mapping? I mean,
so that was
and what did you map it to? I mean, was it some library that you mapped it to?
so, like, yeah, so in that is a circuit minimization technique. So there has been, like, a set of different small.
No, I'm asking that why does technology mapping help?
Why
I mean, is it just, I mean,
yeah, that is just a bit blasting technique. So it takes in the AIG and makes a compact CNF out of it.
so it's just some logic optimization.
Yeah.
And you didn't tell us what Arjun is.
Oh, so that is a preprocessor, and like, so
What does it do?
the Arjun is the preprocessor for model counting. So it looks into it tries to minimize the CNF that is given, that is CNF for model counting. Now Arjun tries to, like, separate out the input variables and output variables. So the case is, like, in case of a model counter like approximC, like, if you know that which are the input variables, if you look at the CNF as a circuit, then if you know which are the input variables, then you can minimize the input CNF. So Arjun tries to find out these variables, like what is the input variables and output variables. and minimizes the CNF so that CNF becomes simpler for model counting.
I think in the interest of time, we'll take subsequent questions offline. Thank you so much, Arjit Shah. The next speaker is Nitesh Trivedi from IIT Kanpur. He's going to talk about data-driven methods for invariant learning on probabilistic programs. Over to you, Nitesh.
Thank you. So I'll be presenting this with data-driven invariant learning for probabilistic program. It was published in CAP 2022. It received a distinguished paper award. So I'll start with a game, a foolish game. So basically, one of rich friend of mine, Mr. Fool, he comes to me every day with a different biased coin, and he tosses that coin until a tail appears on the coin. So for each time the head appears on the coin, he gives me $1. So this happens on day one. And then another friend of mine, who is Mr. Annoying, he keeps on asking me this question, how much do you expect to win today? Subsequently, this happens on the day two. Now, I don't answer to Mr. Annoying because I'm getting some money from, so why do I care? So Mr. Annoying tries to formalize this whole scenario in the form of a probabilistic program. So where this program is parameterized over P, probability P, X represents the coin tosses, N represents the reward that I get, and here X samples from Bernoulli distribution with probability P. So now Mr. Anand executes this program with probability P equal to 0.5 three times, and he gets three different outputs. Then again with probability P equal to 0.3, again he gets three different outputs. Now, Mr. Annoying is really annoyed. How do we reason about such programs? How do we even talk about the correctness of such programs? So one of the ways is to annotate these programs in the form of pre-expectations. So these pre-expectations are basically the expressions that evaluate to real values on the input states, and the post-expectation. So in this case, which is N, and if we are able to find invariant for this program, then it serves as a proof of correctness for the probabilistic program. So in this invariant, this bracketed notation is basically the inversion brackets. It evaluates to 1 if X is not equal to 0, otherwise it evaluates to 0. So our problem statement is, given a loopy program of while G and where G is the loop guard, and P is the body of the program, and a post expectation, post E as input, we aim to develop an algorithm which can automatically synthesize invariants for probabilistic programs. So this is the overview of our tool. So our tool operates in three phases, which is estimation, learning, and verification. So in estimation, we basically sample some initial states, and from these initial state, we execute the input probabilistic program for n runs of times. And then we basically, for each of these n runs, we take the average value of the post expectation corresponding to each initial state. Then in our learning phase, we feed this data to the learner, and our learner is the model tree, which is a generalization of the decision trees, where the internal nodes of the tree are basically the Boolean splitter predicates, and on the leaves resides our model, which encodes our invariant. We extract this invariant out of the model tree, and next we feed this invariant to our verifier module. Our verifier module tries to verify this invariant. If the invariant, if there is a counterexample, then the counterexample state is again passed to the sampler to sample more data. Otherwise, if there is no counterexample, then the invariant is verified. Right. So to verify invariant, so any invariant, to be a valid invariant, it has to satisfy two conditions, which are boundary and invariance condition. We basically encode these conditions in our verifier as an optimization problem, and we generate counterexamples. So not just any counterexample, we generate worst counterexamples. So by worst I mean, so in this figure, if we see this dashed line, tries to separate, is a model which separates red region from the gray region. So these stars represents the points in the red region, and these black dots represent the data points in the gray region. And this uh, green boundary star is a counterexample. But the problem with this counterexample is that it's very close to the decision boundary. And what we do, we generate multiple counterexamples that are basically far away from the decision boundary, which create huge loss for our learner to converge more quickly towards the valid invariant. So, right, so we implemented our approach in a tool called Exist. It's in Python. And we have evaluated our tool on 18 benchmarks that have been collected from previous works. We have found that our tool was able to synthesize invariants successfully for 14 of them, and most of the time that our tool spends is in the sampling phase where it generates data, whereas the verification verification and the learning time is quite low. So, right, so we have here we present some of the programs, some of the program on the left, and the invariants that our tool synthesized for these programs. So right, so we can see that we are able to synthesize nonlinear piecewise invariants, and so we presented a general algorithm exists that is capable of learning invariants, the exact invariants, and it also has the subinvariant part, which is, in the interest of the time, we could I could not discuss this, but if somebody is interested, can definitely go to our paper and read about subinvariants. So, so our tool is publicly available on GitHub. If you please give it a try, and if you have any questions, I'll be happy to take them.
Thanks, Nitish. Questions? I have one question. So you said you generate counterexamples which are far off from the boundary.
Right.
How do you exactly go about doing that? If you can comment on that.
Right. So there are basically these invariant conditions that a valid invariant has to follow. So that is, so we basically encode these conditions in the form of, like, they are basically the inequalities. So we pose them as, like, we want to say that, can you give me the set of state for which this difference of the inequality maximizes? Right. So
Thanks so much, Nitish.
thank you.
Up next is Aditya Patil from MIT Vishwashanti Gurukul. He's going to talk about model counting for game development. Over to you, Aditya.
Next slide. Good morning, everyone. My name is Aditya Patil. I'm from MIT Vishwashanti Gurukul from 11th grade, and along with my mentor, Mark Santalucito from Bernard College, today I'm going to present the topic using model counting for game development and quantifying level difficulty. So our problem statement over here is that game designers in the past have actually struggled to strike a balance between game level complexity and game level design. So our hypothesis to solving this issue is using model counting, evaluation of certain diverse playable characters would become easier for depending on the level as well. So popular game which actually does this well is Super Mario. So Super Mario actually has a dynamic level difficulty adjustment, which analyzes certain player performance metrics and looks at targets completed and looks at certain player performance metrics as to enemies killed or resources collected, and on the basis of that, it'll actually change the way the level will play for the player. So if the player is performing poorly, then the level's difficulty will go lower down. And the player is performing quite well, then the level difficulty will also increase. The proof of concept over here is that before we actually started with a complex game like a 2D platformer, we started with the simplest possible 2D game, which is tic-tac-toe, which also operates on the same dimensions as the simple 2D platform as well. So tic-tac-toe test. So during this test, we actually set up 3 different constraints. One was cell occupancy, where a player can only occupy either X or either O, but it can't occupy both these players can't occupy one cell at the same time. Then turn alteration, the number of X moves and the number of O moves must differ by at least 1, which shows that we are showing the correct turn alteration as well. So the number of X moves, so we are defined that X is the number one, the first player starts over here. And single winner, only one player can either win the game of tic-tac-toe, either X or either O can win, but both players cannot win at the same time. So why did we choose SMT solvers, or which are, so they're actually perfect tools to actually analyze game difficulty, because they're because due to this we can add much more complex rules. So if you were to extend this knowledge towards 2D platformer, we can actually add way more factors and way more complex rules towards this as well. And why Z3 was chosen? Z3 uses Python, which is a language I'm quite comfortable with, and Z3 was chosen because over other alternatives due to stronger community support, and also and the time constraint also didn't let me go through other solvers quite thoroughly as well. So in depth, tic-tac-toe is a solve game, so its optimal strategy is already known, and our goal is to actually later on use this Z3 knowledge and extend it to other platform game, the 2D platform as well. So setting up the constraints. So we first started with we created two 3x3 matrices, X for X and O, and we defined that which player can use which cell. And we also later on added a constraint as to each one cell can only be occupied by one player at a time, and both players cannot occupy the same cell simultaneously. So then over here we're defining who starts first. So the number of X moves can either be equal to or at least at most greater than 1 compared to the number of O moves, which means that X will always be going first in this case, in this simulation as well. Then the player actually has 4 different ways it can win a game. So the row wins, column wins, diagonal 1 win, diagonal 2 win. And then if any of these conditions are met, then the code will declare the X as the winner or O as the winner. And again, as the constraints were mentioned before, we can only have one winner as well over here. Now we're exploring all possible. Okay, now constraint number 3, we are trying to avoid all pre-existing solutions. So we want to try getting the maximum number of unique solutions possible. So we do this by actually comparing the previous cell values and comparing with the current cell values. And we try to compare this and try to get the number of maximum unique solutions possible. So you can the maximum number of valid board configuration without any repetition. So exploring all possible solutions. So over here we're looking at the satisfiable, we are looking at the number of if a solution satisfies all the constraints given to it, then we'll count as one single unique solution, and the code repeatedly does this until it runs out of all maximum satisfiable solutions over here as well. Then we are assessing difficulty level over here. So we have solver.push, which is actually saving the constraints which is given to the solver. Then we have total plays, which is the number of valid port configuration, which is X wins plus O wins plus the number of draws. So these all values will be added up, and this will be the number of total plays. Then we have solver.pop, which actually restores the previous state of the function before any constraints were added. This process is repeated twice to actually get X wins and O wins, because both of them will follow different constraints as well. So we are doing this process 2 times. And then finally, the difficulty is calculated by dividing by you looking at the number of X wins and then dividing that by the total number of plays. So these were the test results over here, as you can see. The conclusion from this is that the higher difficulty for O indicates that the first player route stays the same in a traditional game of tic-tac-toe. The Z3 solver is actually a highly effective combinatorial problem solver for such a simple game, and also allows us for a much more precise and for various configurations. And this test provides a good base for our experiment, and also will let us expand this experiment on 2D platform as well. So 2D platformer test. Keeping this test in mind, we moved on with the same concept of a 2D platformer, and with all the initial experiment done with the constraints as well. The grid setup, we started off by setting up 2 rows and 4 columns and set the number of moves for the tank character as 5. And we did this by and we started with setting up the time step constraint and also the cell constraint as well. So now we have set up the initial position. So the tank position starts at 1, 0, and the unique position constraint means that a tank can only move 1 cell per time step. So at time step 1 can move 1 step, and time step 2 it will move 2 steps as well. Movement rules and goal position. The goal position is that the tank at the end of the simulation should reach 1, 2 at the final time step, and at the movement constraint that the tank could either move right or towards the right side, or at least stay at the same place. It can't move left or up as well. Oh yeah, this is the movement constraint. Now counting the number of valid paths. The code then actually iteratively takes the constraints and finds all possible valid paths. Again, like the tic-tac-toe solution, we're trying to look at the maximum number of unique solutions possible over here. So you're trying to exclude all pre-existing solutions from future checks as well. And you're returning a path count as the number of unique paths as well. So total number of valid paths for tanks is 55 over here, the given constraints. So future work, so the same method can be applied for any other character. If you want to try with an agile character, well, the same method can be applied. So ways to optimize model counting solution. In a traditional method, we'll be using a pre-made model counter, and since this was made from scratch in Z3 solver, it is the most optimal way to find to calculate level difficulty, and then also using different factors to get level difficulty as well. Certain factors, enemy fights, boss battles, and even platform density. All these factors also play towards level difficulty, but this is just a base model as to how do paths play a huge level role in level difficulty. Thank you.
Thanks, Aditya, for the nice one. There are questions?
Yeah.
Yeah, I just wanted to ask that both of the examples of games that you took here are essentially what you call them, and they are solved, like they are solved games. They
Yes.
have limited number of possible solutions.
Yes.
So like, I'm just asking, how are you exactly going to scale this to, let's say, a 2D platformer that is a bit more dynamic?
So I'm currently working on a research paper with my mentor again. So one of the biggest problem statements was that how could we actually quantify level difficulty? So using model counting was a great solution because there have already been made a lot of testers, so we can look at various factors well over here. So, but one of the biggest problem that how do you keep the balance between two diverse characters? So you have one character which doesn't have the best movement skills, so it can not jump very high, but it has good fighting skills. But on the other hand, we have a character which moves quite well and does not have a great amount of fighting skills. So how do you bring a balance between them? So we are trying to quantify how difficult for both of these characters with the given constraints, how difficult would the level be for them?
Also, just as like a follow-up question,
Yeah.
don't you think just going to more complex 2D games, the number of constraints would just keep on increasing? So as you said, there can be multiple characters
Yes.
which have different sort of
Yes.
stats.
Yeah.
So like, uh, again, there's a bit of an issue with scalability.
Yeah, again, that's again a big issue. So that's what I was talking about as to in a traditional method, you do the normal model counter, which is not what I did because due to the lack of time constraints, and since Z3 was I knew Python quite well, so I could use Z3. But in a traditional game, there would be various factors, and you could actually assign these factors different weights as to how important they are to each and every level. So suppose a boss battle would be quite important to how the difficulty. So you could assign each of these factors a different weight, and you could apply this in a certain formula as well. So you could just divide all these values by 10 and then times this by 5, and then obviously put a model counting as well over here. So this is another method where you could actually increase scalability of this code as well.
Are there any other questions? Yeah, let's thanks the speaker again. Thanks, Aditya. The next speaker is Asif Iqbal. He is going to talk about unsolvability of planning problems in cyber-physical systems. Over to you, Asif.
Good morning, everyone. My name is Sheikh Asif Iqbal, and I'm a master student at ISCS, and I'm going to talk about explaining unsolvability of planning problems in the context of hybrid systems. Starting with a brief description of a planning problem, it is a planning problem in a hybrid system is a tuple containing domain, problem, and depth. Domain is the hybrid automata representation of a hybrid system. Problem is the tuple including the initial state and the goal state, and depth defines the bound on the planned length. So for in the diagram we can see that is an example of a hybrid system where it is called a warehouse automation system. Here a robot has to manage items, manage the inventories by taking it from one location to another under the influence of continuous and discrete dynamics. So a planning problem for this in this hybrid system would look like a task for the robot to move a consignment from location 7 to location 18, traversing a maximum of 8 cells. Now a plan in the planning problem is an action sequence that leads to an agent from the initial state to a goal state. So in this hybrid system, the possible actions for the robot are to move to left, to move to right, up and down. So the plan would be a combination of all these actions, and a valid execution of a plan is equivalent to a path traversed within this hybrid system. So, but not all planning problems are solvable. Sometimes it can be unsolvable. By unsolvable planning problems, we mean that no plan, no sequence of actions or a plan exists that can lead from initial state to the goal state, given the constraints and the rules imposed by the hybrid automata. So an example of a planning problem due to unsolvable due to the continuous dynamics. In the diagram in the left hand side, we can see that the locations marked in orange require a consumption of larger battery usage, and so before the robot reaches location 18, it exhausts all its battery and thus it gets stuck. On the right hand side, the planning problem is unsolvable due to the discrete dynamics. Here the locations marked in gray are not interactable by the robot, that is, it cannot move in or out of those cells. So the robot gets stranded in the left hand side while its goal location is on the right hand side. So we are particularly interested in such unsolvable planning problems where the continuous dynamics are the main causes. So for our process, we start by enumerating all the paths in the abstract graph structure of the hybrid automaton, and then we do a linear encoding, linear constant encoding of each of the locations in the paths. So a brief review of a hybrid automata for the subdomain containing the location 7, 8 and 13 and their corresponding transitions. For in the diagram in the right hand side, we can see the squares are the locations of the hybrid automata and the arrows are the transitions. In each location, there are certain variables which are within the control of the hybrid automata. Those being those being the variable x and y, representing the coordinates in which the robot is in, and c being the charge variable, which where the remaining charge in the robot. So first these variables get initialized through the init transition, and then when it enters a location, it is under the influence of the first order derivatives of these variables, and depending on that, the values of the variables change. And in order to stay in a location, it has to satisfy the invariants posed within each location. For example, for location 7, the invariants are x is equals to x should lie between 0 and 1 and y should lie between 1 and 2. And for from each, after staying in a location for some time, it can take a transition to another location, and that would require satisfying the condition given as guard. So for example, taking this transition from location 7 to 8, it has to satisfy x is equals to 1. And so this hybrid automata representation can be transcribed to the linear constant encoding, which we do, and that is done with the help of additional variables, that being the in variables and the out variables. In variables stands for the variables when the robot enters into a location, the values, and the out variables stands for the values when it goes out of a location. And also there are t variables associated with each of the location. T variables represent the time it stayed in a location. So t, as we can see, that t variables must be non-negative, and then for the initial assignment of the variables, we do the following uh, encodings. And then for flow, which describes the evolution of the variables, it is given with the help of these linear equations, where time stayed in the location into the rate of change of the variables. Similarly, the guard is given with the help of a equality condition, and the invariant for each of the locations needs to be bounded for both the in variables and out variables. With this linear encoding, we do the conjunction of all the constants constitute the path formula, which we check for satisfiability using an SMT based solver like Z3. And satisfiability means there is a trajectory from the initial to the goal location, but unsatisfiability means that no valid plan exists. So we try to find exactly why there is no such a plan. For that, we do a finer analysis by breaking the path into several components. The component starts from the initial location to some location Li. For example, the subpath location 7 to L8 and the subpath location 7 to location 9 following the location 8. And for each of these subpaths, we do the linear constant encoding and do the satisfiability check. If some subpath is found unsatisfiable while the preceding one was satisfiable, then we can conclusively remark that the last transition was not being taken. So and the second last location is associated with the last transition, so we focus on that. In the previous slide we saw that location 16 was not reachable from the location 10, so we start by relaxing location 10 and we move back. By relaxing we means altering fixed parameters to some variable range, and that is loosening the constants. So in the left hand side we had the original encoding for location 10, which was c equal to minus 4 into T3. Here the minus 4 is the fixed rate constant, and then in the relaxed state we have modified to it a range from A to B, and C dot being the rate of change of the variable. And then with this modified location we do the satisfiability check for the entire path again, and if it is found satisfiable then well and good, and if it is not satisfiable then we move back to the previous location and continue the process. We continue this process until the path becomes satisfiable, or if it cannot be done then we move to the next path. So if it is found satisfiable, then we record all the locations where the modifications were made, and we say that these locations constraints were too strict and causing the charge depletion in a much larger rate, and so we offer these locations as an explanations. So for example, the location 8, 9 and 10 are offered as explanation. So our approach was tested on few examples, few domains, and we saw that it could find an explanation in most cases. Sometimes when the 6 cross 4 domain where there was an explosion of states, so within the time bound of 1 hour it could not find an explanation. Otherwise in other cases it could. And also in this case where location, in this case there are a lot less paths, but those paths were all longer, and for that reason it could not find any explanations. And most of the time was consumed for the linear encoding and the satisfiability check and the relaxation, but the path enumeration time was significantly less. So that's all. Thank you.
Questions?
What are the advantages of using this SAT-based approach over A star or something very direct?
Well, SAT based, we can, for the SAT based approach, we can scale it in a much nicer way. So that's an advantage. A star would require the complexity would be so high that it would not be practical for problems of this scale.
Can scale because of this relaxation, or
No, SAT-based encodings are SAT-based SAT solvers are already so optimized that it can solve much bigger problems. But yeah, so that's why we have chosen for that.
have you compared it in?
No, we hope to do in the later stages. So this is only an initial project.
Thank you.
Any other questions from the audience? Okay, let's thank the speaker. Thanks, Asif. This is the end of the session. We'll break for the coffee, unless there is. See you after 15 minutes for admin talk. Thank you.